This video will be about all of the intro topics we need in relation to gas laws. The goal here is to give you lots of the notes on gas laws so that in class we can do the demos and the interactive parts so that we can get into the lab more often. So this video will focus on the kinetic molecular theory and introducing the three gas laws, Boyle's, Charles, and Gay-Lussac's. So to start with, we've already talked about gases in our last unit and about how gases have essentially no IMFs. And because they have no IMFs that are exhibited, right, they're all broken, essentially it doesn't matter what the compound is because the IMFs don't matter anymore. So regardless of the gas, their pressure, their temperature, the amount of gas present, and the volume dictates the properties that the gases will exhibit. Okay, so in this unit, sometimes we use carbon dioxide, sometimes we use oxygen, sometimes we use hydrogen, and it doesn't matter what gas we're choosing, they all behave the same. The thing that will change the behavior is changing the pressure, temperature, their amount, or their volume. Now this slide says that the properties are based on the kinetic molecular theory. So we're going to now talk about what that means. The kinetic molecular theory is a theory based on the fact that the gases are in constant random motion, right? They're moving around like crazy with a lot of energy. And because they're moving around like crazy with a lot of energy, their behavior is described by motion more than anything else. More than their chemical structure, more than their type of bond, their behavior is described by motion. So kinetic molecular theory says that all gases are in rapid, constant, linear motion. So gases are always moving forward, right? And they're always moving forward until, the second part, they're going to change directions if they hit something. So if they hit a wall or another gas particle, they will change directions, okay? And then the third part of the kinetic molecular theory is that all gases that we mathematically talk about or that we encounter, they're assumed to be ideal. Okay, so essentially the kinetic molecular theory again says that because things are in constant random motion and they only change directions when they hit things and they act in an ideal fashion, that's going to explain all of the behavior that we exhibit. Okay, KMT explains why when you open up a bottle of something like perfume, why the odor eventually gets to you, right? The gas molecules are in constant random linear motion. They're changing direction when they hit things, but essentially they're going to eventually get to your nose. Okay? They also explain why if you put dye into water, eventually that dye will completely disperse evenly throughout the substance, even if you don't mix it. Okay, so the kinetic molecular theory really applies to any state of matter, but because gases are in so much motion, we usually talk about it in relation to that. Now the third part, gases act in an ideal fashion, you have to be able to know what that means. Okay, so the kinetic molecular theory is three pieces. They move straight, so they hit stuff, and they act ideal. And then what does being an ideal gas mean? Well, an ideal gas means that when they hit each other, when gases hit each other, they hit in an elastic fashion. So elastic means they hit and bounce off, but they don't break or stick, right? It's a difference between a ball hitting the wall and bouncing versus throwing two sticky things at each other, like two pieces of Velcro, and they hit and they might stick. Okay, so for gases, they hit and bounce off, which is elastic. Inelastic means they hit and stick. So that means no energy is lost in the collision. Energy might be transferred. So if you hit one thing onto another, that might go forward like a pool ball. You hit one ball into the other one, that might accelerate that new ball forward, but the balls don't break, or they don't stick to each other. The other part of an ideal gas is that there are no IMFs, right? No attractive forces. And that's essentially because they're moving so fast, they don't have enough time to stick to one another. And the last part of an ideal gas is we essentially, when we talk about the volume of material, we don't actually talk about the volume the particles take up in themselves. We talk about the volume of space that the material fills. What I mean by that is gases are so far apart that essentially they're not even touching or interacting. So their volume that they take up themselves, like each individual atom, doesn't matter. Okay? So when we talk about volume of gas, we don't really talk about the actual molecule of gas itself and the volume it takes, but more the entire space the gas is contained in. So again, the kinetic molecular theory is that gases move straight till they hit stuff and they act ideal. And what it means to act ideal is that they hit in such a way that energy is transferred but not lost. There's no IMF. And when we talk about volume, we're talking about the total space the gases are taking up, not the volume of the actual particles. Now, we use this word ideal versus real. You are surrounded by gases around you all the time, and those gases are acting in an ideal fashion. Under normal temperature and pressure conditions, gases act ideally. In reality, if you decrease the temperature a lot or increase the pressure a lot, they can start to act in ways that contradict this ideal gas thing. So like maybe they start to stick a little. Maybe their particular particulate volume starts to push back. And so you can break this ideal gas rule if you change the conditions. But in general, for us, at the pressure and temperature we're at in normal room state conditions, all gases act in ideal fashion. The next part of the unit is about gas laws. And the gas laws are laws that exist for gases as it relates to pressure, temperature, and volume and how they relate. Okay, so gases act based on kinetic molecular theory. But again, when we look at gases then, it's not about what the gas is. It's about these different variables and how they interact. Okay, so there's 3 laws you need to learn: Boyle's law, Charles' law, and Gay-Lussac's law. So Boyle's law is first, and as Boyle was interacting with gases, what he noticed was that any time you kept the temperature of the gas constant, so you did not allow the temperature to be variable, then if you changed pressure that was applied to the gas, you would guarantee to change the volume. Okay? And it was in such a way that as you increased pressure, you decreased volume. So there was an inverse relationship with those 2 variables. As one goes up, one goes down. And essentially, the equation we use for Boyle's law is the concept that if you had an initial pressure and volume of gas, if you affect one of the variables, the other one will change also, but it will keep the equation equal. Right? So it'll change in such a way proportionally so that the conditions are equal at the beginning and the end. So pressure and volume are an inverse relationship. As one goes up, one goes down. So if you increase the volume that the gas is contained in, you decrease the pressure. So here's a small simulation of what this looks like, right? I'm increasing the pressure on the system by putting more weights on it. And as I increase that pressure on the system, I'm decreasing the volume, right? So that is the inverse relationship you see there, and you see how the graph looks like an inverse relationship. So again, as volume goes down, pressure goes up. That's what these graphs look like. Charles' law relates volume to temperature, and what his relationship was is that as you increase temperature, the volume of the gas always increases as long as you keep pressure constant. Okay, so in all these cases, all these laws, you take one variable and hold it constant, so pressure is not allowed to change. And then if you increase the temperature and want to keep pressure constant, you have to increase the space the gases are taking up. So this has a directly proportional relationship. If you have an initial condition, when you change the condition, it'll stay equal. It's just that both variables will go up or both variables will go down. Okay, so this equation down on the bottom, this is V1T1, so that's an initial volume and initial temperature, and that's going to equal, if I change one of them, if I change my temperature to a new temperature, T2, volume will also change. And I'll show you guys the math of this in class. I just want you to get the notes here. The directly proportional relationship of this graph shows a linear relationship, right? As one goes up, the other one goes up. So this is what a graph would look like of Charles' law. So we've already looked at pressure and volume and temperature. So the last one we look at is pressure and temperature, and that's Gay-Lussac's law. So his was the last one. They were all kind of working around similar times. But for him, then, if you don't change volume and you allow pressure to change, now what we find out is you increase the temperature, you increase the pressure. So if you don't allow the volume of the container to change at all, an increase of pressure in the system will result in an increase in temperature in the system will result in an increase of pressure. Okay. Again, because of this relationship, proportionally up, right? They both are directly proportional. As one goes up, the other goes up. Graphically, again, you have a linear relationship, whereas one goes up, the other goes up. So that's it for this video. I just want you to get the content down for kinetic molecular theory and the 3 gas laws. In class, we'll go more in detail on this, reflecting on these gas laws in the lab. We'll do some actual data gathering with Boyle's law. We have lots of, and then we'll actually do math with these too, right? One thing to note, and it was on these slides, is that when you're dealing with temperature and gas laws, the temperature has to be in Kelvin, and that's because you can't end up having a negative relationship. If your temperature goes below 0 to a negative Celsius, you would then end up probably calculating like a negative pressure, and that is not allowed, right? There's no such thing as a negative of pressure. So Kelvin, with its absolute 0 scale, allows us to manipulate these equations as such. So go ahead and do the form with this video, and then have a nice day.